Welcome back, folks. Mr. Johnson with you once again. This is a lecture on Le Chatelier's principle, or Le Chatelier's principle, if you don't speak French well, with a quick intro on equilibrium and how it is established. All right, so as a quick review of the concepts you learned in those College Board lectures about equilibrium and how it's established, I want to remind you all that equilibrium exists when the rate of the forward reaction equals the rate of the reverse reaction. Again, equilibrium is established or reached when the forward reaction rate equals the reverse reaction rate. As we look at this diagram here on page 101 of our physical textbook or 109 of our ebook, we're looking at a system where reactants A and B form a product AB. It's a synthesis reaction here. If all there is to begin with are reactants A and B, substances A and B, then the only possible reaction would be the forward reaction. And assuming that the concentration of reactants A and B are relatively high to begin with, let's say, then the rate of that forward reaction might also be relatively high, because rate is proportional to concentration. The long forward pointing arrow is indicating that the forward reaction rate is the only reaction that's occurring, and it's a relatively high rate because that arrow is relatively long. But as that reaction occurs, and as reactants A and B form product AB, there's a lower concentration of reactants A and B. And as the concentrations fall, the forward rate also falls. Again, concentrations are related to rate. We see that depicted in stage 2. The rightward pointing arrow, indicative of the rate of the forward reaction, is shorter. The forward reaction rate has slowed down as reactant has been converted to product. But of course, as the product is accumulating, and the product is the reactant for the reverse reaction, as AB is accumulating and its concentration is increasing, the rate of the reverse reaction starts to increase. As the rate of the forward reaction is decreasing and product is being formed, the rate of the reverse reaction increases. There becomes a point at which the forward and reverse rates equal each other, which is represented by stage 3 here, by the length of the rightward and leftward arrows being the same, and that's when equilibrium is established. That does not mean that the concentration of product AB is the same as reactants A and B. It just means that the forward and reverse rates are equal. Their concentrations, again, may not be equal at equilibrium. In fact, that would be very coincidental that that would be the case. As we scroll down, we see a graph depicting this same system, but this is the changes in concentration over time, not the changes in rate via the length of these arrows. And we see that to begin with, all there is A and B. There is no product AB. And as A and B fall, AB rises. When these concentrations level off, which is at about time 6, or maybe 6.2 or 3 seconds, when the concentrations level off, that's when we know equilibrium has been reached. And in this case, notice that the concentrations of A and B are not the same as AB, which they aren't necessarily at equilibrium. In this case, there's ultimately more product at equilibrium than there is reactant. And again, that was a quick summary of what from the first 2 College Board lectures about equilibrium you have begun to understand. I've flipped my book now to page 108 of the physical textbook, 116 of the ebook. We're in section 2.2, Le Chatelier's principle, looking at the section called equilibrium response to adding or removing chemicals. This is all about if a reactant or a product is added to an equilibrium system, what will happen? How will that system respond? And Le Chatelier's principle, which is one of the easiest often once you get it to understand principles and widely used in chemistry, is this. An equilibrium system subjected to a stress will shift to partially is a key word in here, alleviate the stress and restore equilibrium. Again, Le Chatelier's principle says that an equilibrium system subjected to a stress will shift partially to alleviate the stress and restore equilibrium. We'll learn what those stressors can be, what in general a stressor and what the specific stressors are we have to be comfortable with in here. Well, the first stressor is either adding or removing reactant or product. And if we look down here in reddish orange, it says that when a quantity of a reactant or product is added to an equilibrium system, the system will shift to remove some of that added chemical. Or when a quantity of reactant or product is removed from an equilibrium system, the system will shift to replace some of the removed chemical. And those 2 statements meet the criteria for Le Chatelier's principle because Le Chatelier's principle says if you add a stressor to a system, the system will shift to reduce that stress. Meaning if you add a reactant, the system will respond in such a way to get rid of some of that added reactant. Or if you remove product, for example, the system will shift in such a way to regenerate or to restore some of that removed product. About to take you now to a video that will give you a really nice visual example of how Le Chatelier's principle plays out in real life in chemistry, and we'll come back to our book. Sit back, relax, and enjoy this YouTube ride. After 5 failed attempts of inserting the video into this recording with good audio, I've given up. So watch this video on YouTube. The URL is here at the top. So take a moment to grab that URL if you want. Or if in YouTube you enter Chemistry with Dr. H, it's the 3rd video down, this Le Chatelier's principle video. So Chemistry with Dr. H, 3rd video down, and you're meant to pause it at 3:47. So if you want to pause the video at 3:47 and then jump back to this main video, you can. If you want to watch the whole thing, of course, you're welcome to do that as well. So now I want to talk about a couple of terms that were brought up in that video, and then we'll do a couple of practice problems using Le Chatelier's principle, and then we'll talk about why this happens, because that's interesting as well. So you heard the narrator talk about the system shifting to the right or shifting to the left. Those are common terms that we use when we talk about equilibria changes. If more reactant is being converted to product, and that's the forward reaction, by the way, then we say that that's a shift to the right. If, though, more product is being converted to reactant, that is the reverse reaction happening at a greater rate, then it is a shift to the left. So shift left and shift right, again, is a way that we talk about an equilibria system changing often. So we flip the page. We're on 109 now of the physical textbook, 117 of the ebook, looking at sample problem 221A. Question says, some HI is added to the system below. In what direction will the system shift to restore equilibrium? And when equilibrium is restored, how will the concentration of each substance compare to its concentration before the HI was added? So we're adding HI. First thing we do is recognize that HI is a product, and that if you add a product, the system will shift in such a way to remove some of that added product. Not all, but some. That means that the reverse reaction will occur to cause that to occur. This system will shift to the left to get rid of some of the HI that's being added. So it's going to be a left shift, and we see that here in green. And then if it's shifting to the left, remember some of the HI that was added will be converted to reactant. So there will still, at equilibrium, be more HI than there was to begin with. Remember, we're adding HI. Some of the added HI is converted to reactant, but not all of it. So ultimately, there'll be a little more HI in the end than there was, and there'll also be more H2 and I2. There'll be more reactant because some of the product, not all of it, but some of it is being converted to reactant. So there will overall be an increase in the concentration of HI, the product, and both of the reactants. I flip my page. I'm on 118 of the ebook, or 110 of the textbook, looking at practice problem 221 here, highlighted in blue. I recommend that you try this on your own. Pause the video, read through question 1A, B, and C, answer this in your book, and then come on back and see how your answers compare to mine. All right, A, what does Le Chatelier's principle say will occur if some iron nitrate is added to the system? We're essentially adding iron ions because the iron nitrate dissociates. Well, the system will shift in such a way to reduce the stress of adding iron ions, to reduce the stress of adding a reactant. The system will shift in such a way to remove some of the added reactant. That means it'll shift to the right. So as I go to B, in which direction will the system shift? It'll shift to the right. If I look at C, when equilibrium is restored, how will the concentration of each substance compare? Well, if we're adding reactant, we know it shifts to the right. Not all of the added reactant will turn into product, so there will still be a greater concentration of iron ions in the end than there was. But because there's another reactant, the thiocyanate ion, that wasn't added, because this system is shifting to the right, there will be a lower concentration of the other reactant, the SCN ion, in the end when equilibrium is established. Iron concentration will be higher, some was added, and some of the added iron is removed. SCN will be lower, and then the product, the FeSCN2 plus ion, will be at higher concentration. Iron ion will be higher, SC ion will be lower, and FeSCN2 plus ion will be higher when equilibrium is established. I've scrolled down, I'm on the same page looking at practice problem 3 here in green, and I'm going to jump to the whiteboard and solve this one with you / for you. All right, so we got a graph below with I2, H2, and HI depicted. Those are the reactants and the product. H2 was suddenly added to this closed system. Equilibrium was reestablished. complete the plots to show how the system would respond, what the concentrations of the reactants and products will be relative to what they were to begin with. Notice there's an instantaneous increase in the concentration of H2. When a reactant or a product is added, there will be an instantaneous increase in that substance. So if H2 is being added, which is a reactant, the system will respond in such a way to remove some, not all, some of that added reactant, which means it will shift to the right. So we're going to see more product being formed and some of the H2 that was added and the I2 that is still there decreasing in concentration. I'll show you what those lines will look like. All right, in fact, we see the two reactants, concentrations falling, and because they both have coefficients of 1 or the same coefficients, their concentrations should fall at the same rate. Those lines sort of mirror each other. Meanwhile, the product, as the reactant concentration is dropping, will increase, but because there's a 2 in front of HI, its concentration should increase at twice the rate that each of the two reactants is decreasing. And notice that that's indicated via this blue line going up at a faster rate than the red and green lines were going down. Ideally, all these lines flatten out at about the same place because equilibrium should be established when the reactant and product concentrations remain static, and that again should happen for all three substances at the same time. I didn't do a perfect job depicting that, but I'm okay with how it is. All right, flip the page. We are now on page 119 of the ebook, or 111 of the hard copy textbook. I'm reading this sentence to you in purpley pink. Le Chatelier's principle, so far, has only described what happens when a reactant or a product is added or removed. But it doesn't explain why. And that's where it gets interesting. It doesn't explain why. Well, if we read in yellow, it says that to an equilibrium system, a stress, in this case, to us a stress is the addition or removal of a reactant or a product, is any action that has a different effect on the forward rate than it has on the reverse rate. If you cause something to occur that affects a forward rate differently than a reverse rate, then the equilibrium will be shifted, either to the left or to the right. So let's explore that, the why, the mechanism. And it's based on things we already know about collision theory. It's based on things we know from kinetics. We're looking at sample problem 2.2a here in green, describing the shift mechanism. It says to explain in terms of forward and reverse reaction rates. Meaning we've got to refer to the relative forward and reverse reaction rates, how the following equilibrium system would respond to adding some iron 3 chloride. Iron 3 chloride, meanwhile, dissociates into iron ions and chloride ions. So if we're adding iron 3 chloride, in terms of this system, we're essentially adding iron ions, a reactant. We know that that will shift the equilibrium to the right. There'll be more product formed than there was to begin with. Well, this is all about collision theory. If you're adding more iron ions, there's an increase in the concentration of iron ions. There's an increase in the concentration of one of the reactants. If we imagine the rate law for the forward reaction being rate equals K times iron ions, in brackets, concentration, times the thiocyanate ions, if you raise the concentration of the iron ions, the rate will go up. But just the forward rate to begin with, because all you've added are reactant ions. When you add iron ions, the forward rate increases, whereas the reverse rate doesn't. And that, now that the forward rate is greater than the reverse rate, causes the system to shift to the right. Now, we know, as more and more reactant gets consumed, and more product gets generated, the forward rate starts to slow down a bit, the reverse rate starts to speed up, and at some point, they meet each other again, and equilibrium is reestablished. So in the case of adding a reactant or adding a product, you are increasing the rate of the forward or reverse reaction because you're changing the concentration of ions. There's a greater chance that particles will collide, collision theory, and the rate goes up. Again, in this case, adding iron ions will increase the forward rate, and therefore the system will shift to the right. And down below, same page, figure 2.2.1, is a nice depiction via these two graphs of that shift mechanism. Again, at equilibrium, this is prior to the addition of iron ions, the forward and reverse rates are equal, indicated by the left and rightward arrows being the same length. The moment that reactant is added, iron ions is added, the forward rate increases. The reverse rate doesn't. The forward rate arrow is now greater than it was. As time goes on, though, the forward rate drops. As reactant is being consumed, the reverse rate increases. And at equilibrium, the forward and reverse rates are equal, and they're both greater than they were because there's now more overall substances in the system, causing, again, the reverse and forward rates to be equal. but to be greater than they were before. That's shown over here in 221b, where when reactant is added, the forward rate goes up. Then, as reactant is being consumed, the forward rate decreases, the reverse rate increases, and eventually they find each other. Because this is rate on the y-axis, at equilibrium, those two lines should meet because the rates of the forward and reverse reactions at equilibrium are the same. If this were concentration on the y-axis, of course, those lines would flatten out, but they wouldn't necessarily meet each other. And then off to the right, at equilibrium initially, forward and reverse rates are equal. That's the top row. Once the product is added, the reverse rate increases. That's the lengthening of the left-hand red arrow. And then as time goes on, forward rate increases, reverse rate decreases, and again, they find each other, bottom box. All right, last concept is about the role that catalysts play in equilibrium. We know that catalysts are substances that can be added to a reaction that lower the activation energy by providing an alternate mechanism or pathway and therefore increasing the rate. Well, catalysts do that equally to the forward and reverse rates. Adding a catalyst increases the forward and reverse rates equally such that there's no effect on the position of equilibrium. One last time, catalysts increase forward and reverse rates equally such that there's no change on the position of equilibrium. That's it, folks. Part 2 is coming to you next, which looks at how equilibrium systems respond to volume and temperature changes. And it's based on a lot of the same stuff we talked about today. Look forward to seeing you in part 2 in just a bit. Take care. Be kind. Love yourself and those around you.